Right now, two massive climate forces are colliding. We are becoming increasingly reliant on solar energy to power our lives, right as extreme wildfires occur with greater frequency. Across the country, we are rolling out massive utility-scale solar infrastructure. It's a core piece of transitioning the grid away from fossil fuels. But the atmosphere above that infrastructure is changing. Wildfire smoke is becoming a dominant feature of our skies, routinely drifting over major solar installations. The physical assumption here seems obvious. Since the aerosols in wildfire smoke physically scatter and block photons of light, solar panels sitting under a thick blanket of smoke should produce noticeably less electricity. If that physical assumption holds true, the collision between rising wildfire activity and solar deployment presents a serious threat to the core reliability of our clean energy transition. To track exactly how much power we are actually generating, researchers look at the U.S. Energy Information Administration's EIA 930 data. It is the standard public operational record for the national power grid. But when economists checked the data for those highly smoky days, they found something incredibly counterintuitive. According to the public records, on days blanketed by wildfire smoke, grid solar generation actually goes up by 6 to 7%. This chart of official public grid data highlights the problem. The bottom left plot shows a clear positive association. When smoke exposure hits an entire region, the observed solar generation increases, which forces us to ask a strange question. Are grid operators somehow pulling extra electricity out of thin air, or does thick, blocking smoke actually benefit solar panels? Trusting these operational records at face value misstates how the grid actually responds to environmental hazards. This statistical shift is driven by a specific meteorological state: fire weather. Major wildfires do not happen on rainy, overcast days. They ignite and spread when local conditions are hot, bone dry, and completely free of cloud cover. Thick rain clouds block vastly more sunlight from reaching the ground than even a dense plume of wildfire smoke. This creates a conflation in the public data. Because severe smoke days are almost universally cloudless days, the solar panels end up generating more total power than they would on a typical, overcast afternoon. The grid's official operational records only measure what happened, that high power output. They fail to record why it happened, ignoring the fact the underlying sky was perfectly clear. That beautiful, cloudless weather acts as camouflage. It masks the physical penalty caused by the smoke itself. To find the truth, researchers had to build a specific physical resource layer. They needed a way to mathematically strip away the weather and isolate just the smoke. They used a technique called a clean reference. They matched a smoky day at a specific solar plant with an identical day at the exact same plant, time, and season, except this reference day had 0 smoke and 0 clouds. This data from the EPA and NASA shows exactly how they verified those conditions. The top left chart proves that ground monitors strictly validated the light, medium, and heavy smoke classifications used in the study. Looking at this isolated resource data, the first major finding appears on the left chart. Heavy smoke drops the overall ambient sunlight reaching the ground, a metric called global horizontal irradiance, by roughly 5.5%. But it gets worse. Direct beams of sunlight, direct normal irradiance, plummet by a massive 22.2% under heavy smoke. Once the background weather is stripped away, we can see the penalty clearly. Dense smoke physically starves the panels of the light they need. So what happens when researchers apply this newly isolated, true physical drop in sunlight back to the regional grid operations? These charts at the bottom show the paradox completely reversing. When measured properly as a resource shock, observed solar generation on the grid actually falls significantly during major smoke events. And there is an immediate operational consequence. To make up for this sudden, unrecorded drop in solar power, grid managers are often forced to spin up secondary fossil fuel generators just to keep the lights on. The planners designing our future decarbonized power systems rely heavily on historical grid records to predict resilience. They look at past data to figure out how much stress the system can take. If those planners only look at the raw grid data, they will wrongly view smoke days as favorable for solar generation. That means they will drastically underestimate our vulnerability to extreme climate events. Building a resilient power system requires integrating these physical climate layers with our operational records. Relying on grid data alone leaves the risks of extreme smoke hidden within the very datasets we use to measure them.